All right, we're going to move right along into our next session. So I'll introduce myself first. My name is Dan Westervelt. I'm an associate professor at Columbia University in New York. And we have 4 talks lined up today in this session, which the title of the session is Making Sense of Sensor Data. So our co-chair is Dr. Collins Hodoli from UESD in Ghana. He unfortunately could not make it. So we have Miss Josephine Kenyaria from Jomo Kenyatta University, who will be co-chairing.
Hi everyone, my name is Josephine Kenyaria of Jangwi, my surname. I'm a student at Jomo Kenyatta University. I'm also working with an organization called IRINEX Solutions that deals with environmental impact assessment, environmental audits, and air quality assessments. Thank you.
So I think we'll have our speakers give their 15-minute presentations, and then we will save questions for the end, just like all the rest of the sessions have been doing. So our first speaker is Dr. Solomon Otu Lamote from UESD. So if we can get his slides up. I'll let you introduce yourself while I get the slide.
Good afternoon to you all. My name is Solomon from University of Environment and Sustainable Development in Somanya in the Eastern region. Well, today I'll be presenting on the PM 2.5 levels on understudied area in the rural Ghana using relative loss cost sensors. So, next slide. Well, the outline of our presentation, we'll talk a little bit about background, especially the motivation of this research that is still ongoing, and then why the focus of using PM 2.5. I think a lot of people have presented on PM 2.5, so I will not speak much about it. I think basically everybody is aware about it. Talk a little bit about the methodology and data analysis that we employed, and show some preliminary results of our sensor that we have recently, and then some limitation and take home questions. Well, air pollution is one of the key risks. I think our professor from Nigeria made a lot of comments and suggestions towards the health risks of air pollution to our health sector and the community in large. And this is the reason why within the rural community in Ghana, especially in the Eastern region, it's very important for us as a university, because our university is a university of environment. However, our main goal is to make sure we sustain the environment. And then in the department where I'm coming from, and the group is coming from, the built environment that's involved the architecture and design, and then the civil engineering, construction, and urban planning. They really need this information of air quality monitoring and forecasting to know how they could reduce or use certain materials to mitigate the air pollution within this region. And this is the reason why most of our time in Eastern region, especially, we don't have sensors. So it's recent time, I think it's early in March or first week of March, we had a low-cost sensor, which is the AirNote. And we don't have a lot of expertise in this area, especially in the university where we are in the Eastern region. And this creates a lot of gap because it was presented by our professor from University of Ghana. They have the hub. What about the Eastern region part of Ghana? So that's the motivation towards why we intend to undertake this research. Next slide. Well, this slide has also been showed by other scientists here, showing the deployment of the air sensors in monitoring air quality. And we can attest the fact that on the African continent, we have less sensors receivers, or so I say instruments to monitor this air quality. So our main goal as a university is also see how we can increase the capacity of these sensors over Ghana to be able to get good data-driven hubs. Next slide, please. Well, as I said earlier on, we just recently received an air sensor, that's the AirNote sensor. And on my figure on my far left shows the circuit board, and then the SIM card section where we have the card is being slotted. And then when we mount it in the case, and then on my far right shows where we installed the sensor over the university campus. And next slide, please. Well, so this is a map that shows the eastern part of Ghana, showing where our sensor is being installed on the university campus. We cannot attest the fact that the previous speaker in the beginning, we can see a lot of deployed sensors Looking at the eastern region, we just have only one at the moment. And then doing air pollution study with only a single station is a difficult challenge. And it doesn't even give you the depict the real air quality behavior within those regions. And this is why we are advocating today that researchers and scientists who are on board to come play so that we can employ more sensors over that region to be able to study the air quality within those sectors. So this a plot that we see from our recent installed receiver for the few months that we had this instrument being installed. We can clearly see from the month of March to April, we have a decrease in the level of the PM 2.5 indices values. And also we can also see that there's a long-term data required to understand this parameter over this region. As I said earlier on my presentation, using a single station is difficult to depict. And this is a low-cost sensor. When we say low-cost sensor, what I want to bridge the gap is, it's not about how much it costs. It's the data that we are looking at compared to the standard as our professors have in the University of Ghana. Next slide, please. So this really depicts to the previous slide showing the peak values of the PM 2.5. Well, on the horizontal line shows the threshold about 15 microgram per meter cube volume. So above this, we can see that how the sector or the eastern region is recording some high values of air pollution within those regions. And then getting to May, that's when we got the data, because that's when we earlier received this instrument, and then this is when the study is being carried on. And I want to make mention of this, that this research is still going, and we are just showing some preliminary results of what we have at the moment. Next slide, please. And we did some trend analysis to see how it is behaving along the years, along the months. You can clearly see that there's a peak centered around 14 UT around this time in March and April, with low that in March, and then April and May, we have very low standard required to the color code that we have. Please, next slide. Well, that's also to understand, we do the calendar plot to see how the air pollution index is increasing in a month, in a day. So we have March, April, and May. We can clearly see from March that we have high indices of air quality or indices within those periods, as I showed in my previous slides, compared to April and then May. And clear patterns of daily pollution level decreases in order of March, April, and May, respectively. Well, this is the diurnal pattern of the air quality that is being observed by the sensor during the week. And this was done by taking various diurnal patterns along each of the months to see how they vary. Most of the maximums occur within the noon time with a slight shift in time, local time. And this really shows that around noon time, we have some peaks around, and this shows that the diurnal pattern of the air pollution monitoring within our eastern region sector show clear maximums around noon, and then with the depletion during night time. This also represents the previous slide showing what we wanted to just explain, elaborate more on the weekly. So next slide, please. Well, as I said earlier on, the limitation of this study is that the limited air pollution data for PM 2.5. To fully understand this monthly variation, we need more instruments installed in this region, and also needed a reference frame. Our intention in the future is to get our standard reference frame to be able to have a co-located sensors, to be able to calibrate them to give good monitoring and forecasting of what is happening within these sectors. Because the university is located in a mangrove region where we have a lot of vegetations, but however, we are recording high indices of air pollution within those sectors. And also, as I said, through a correction factor was applied to improve the raw data that we observed. As you said earlier, the previous speakers made mention of the correction factor to be able to match the data from the low cost to the standard to see whether we are having the same values by comparing to the standard reference frame. And relative low-cost sensors are suitable for establishing baseline levels of PM pollutions. We appropriately calibrate protocols air sensors can be used for understanding 2.5 PM pollutions, and a prerequisite for air pollution management, controlling environment with limited logistics for air quality monitoring. And we, as a university, one of our goals to the community is to engage the community people about telling them what to do to avoid mitigation, to reduce air pollution within the community. So In the near years or 2 years coming, we are creating capacity building workshops, engaging the community people to involve, train them on what to understand about it, because some of them literally will not be people who want to go into academia to understand the physics behind what drives these air pollutions, but they can also be an advocate to the community, telling them that, oh, today or this week, we are having high pollution within this environment, and we need to look at what is leading to this. Maybe deforestation is going within the community, and we have to look at it carefully. So basically, we as a university are advocating to most of the research scientists around who are willing to employ sensors, air quality sensors into a University of Eastern Region to be able to cover the whole sector. Thank you so much for attention.
Thank you for that talk, Dr. Solomon. So a good reminder not to forget about the smaller cities in our air quality studies. We'll hold the questions for the end. And our next speaker, I believe, is going to be online, Dr. Gabriel Okello from Cambridge. If you can hear us, say hello.
Hi all, can you hear me? Gabriel is still connecting. If you can move to the next speaker and come back to him, that would be great.
Okay, sure. So we will go to Garima Raheja from Columbia University, if she can come up.
Hi, everyone. My name is Garima. I'm a PhD student with Dan at Columbia University. A lot of the work I'm going to present today, couldn't have existed without the critical work of many of the people here. So, some of the figures are figures you've already seen or you were very instrumental to creating. I have a lot of figures. So the goal is I will kind of expose you to all of them, and then we can chat more in detail about some of them later if you wish, just because you're probably all familiar with them. I also like to animate my slides, and so I have a lot of slide transitions, but no clicker. So please bear with me as we try to navigate technical issues. The goal overall is to understand air pollution in cities, but we want to use low-cost sensors to do it, and then we want to make sure we can do it around the world, not just in one place. So the techniques we develop, should really be transferable. So what we're going to talk about today is we're going to talk about the motivation and comparing the sensors. And then we'll talk specifically about two cities. So one is Accra, Ghana, and Lomé, Togo will be the other one. And then finally, we'll just talk about some key takeaways and the next steps in this work. As an introduction, we've seen this figure. I think one of the earlier slides mentioned a figure very similar. The number of deaths attributable to air pollution is not equally distributed around the world. And additionally, the number of cities with air pollution monitors is kind of the reverse. So some cities have over 200 air pollution monitors and some have none. So what that results in is a disproportionate, population weighted distance to monitors. And especially if we look in Africa, the borders kind of the borders are the distance to the nearest monitor, and the darkness of the map was the PM 2.5. So when we have traditional monitoring, it's very expensive because we have the instrument, assembly, maintenance, transportation. If you add climate control, et cetera, it becomes almost prohibitively expensive to do that. So we use low-cost sensors as our solution. There's many different types that we can use. And we can bridge the monitoring gap by using, let's go back one slide. It's fine. We can bridge the monitoring gap by using a number of data science techniques to really refine the quality of the data from these sensors. So in Accra, we compared 21 devices for 5 months. That included 1 Teledyne, 16 Clarities, 2 purple airs, and each of the purple airs has 2 channels and 2 Quant-EQ modulars. And the results we got are on the black here is the Teledyne. So we're comparing all of the low-cost sensors to the Teledyne. So we have the 16 Clarity, the 2 different channels from 2 different purple airs, and then finally also the modular. And you can see that they show pretty striking accuracy, but they're not all made the same. For example, the Clarity, let's go back one slide. It's okay. The Clarity have a lot more spread. The modular are a lot more closer to the reference monitor. And all of these figures, are available in the paper if you want to check them out more. But the key takeaway is that the sensors are pretty accurate, but not all exactly the same. We also compared 4 different machine learning models for correcting the low-cost sensors. So the The first two are multiple linear regression, as we talked about earlier today, as well as Gaussian mixture regression, which a number of folks have been using as well. And the idea is to optimize for R squared. So we want that to be really high, and we want the mean absolute error to be very low. So here I've kind of highlighted where that's happening. And then if we go to the next slide, we tried two additional techniques, random forest and XGBoost, and these perform pretty well when you're training the data, but we noticed that when you actually try to use that for sensors out in the field, it wasn't performing very well. So we take those out and we focus on the one that does perform well in deployment, and that is going to be the GMR technique. So if you're interested in using that technique, I know some people are already using it. You can talk to me after and I can send you some code. It's pretty easy to use once you have, once you've, gotten the hang of it. So we're focusing on that one. Also, the intercomparison we did here kind of inspired what you saw earlier today, the AFROSET stations. So we compared a few monitors, and now that effort has really grown thanks to the work of so many people here, Dr. Hughes. So we're going to zoom in and focus just on Accra, Ghana. So we use the techniques I mentioned, we use that to correct the data, and then we actually use the corrected data to understand what's going on in the city. So we monitored them for about 3 years. That's 16 sensors that were deployed. And then we found that the network-wide daily mean was 23.4 micrograms per meter cubed, which is much higher than the WHO's guideline for air quality. This plot is a number of violin plots showing the comparison of the sensors to the WHO daily guideline, which is this dotted line on the bottom. Again, we see that there's a fair amount of distribution, and each of these sites is a site in Accra that you might be familiar with. We also compared the diurnal cycle, so that's the cycle throughout the day from midnight to the next midnight, between the harmattan, which is shown here, and the dark red line is the network mean, so that's the average between all of the different sensors. And then we compared it to like the harmattan versus non-harmattan. So I know there's a lot of information in these plots that you could stare at and look at for many hours and try to figure out what's happening. I guess since this session is about getting actionable data from low-cost sensors, instead of talking directly about every single thing happening in every single plot, I kind of, again, want to remind you that this is just to expose you to the different kind of ideas and data and insights you can get from low-cost sensors, especially a network of them. So just zoom out and think about the big picture, and you can think about the little picture later on if you want to look at the graphs in more detail. We also looked at the diurnal cycle at one specific site and how it changes in and out of the harmattan. So the darker the line, the deeper we are in the harmattan. You can make one of these plots for every single site. And also understand how COVID reduces PM2.5. So here we're just doing it for 3 sites. And there was a huge range, 15% decrease, 23% decrease. Some sites didn't really have a decrease, but also something you can do when you have multiple years of data that span multiple events. This is a map of the city if you want to find where you are. And each pie chart shows the amount of days that were over the WHO's guideline. So the redder the graph, the worse the air quality consistently. And then also we zoomed in just to Jamestown specifically because there's a whole lot of sensors in very high density in that city. And you can see here that even between 2 sites that are next to each other, there can be a huge difference. Moving on to Lomé, Togo, just across the border. You can read more about this on a paper that Professor Sabi and Sonla contributed greatly to, and then also, look out for Sonla's paper that's coming out very soon. That's a follow-up to this and really builds on a lot more work that has happened since this paper came out. So we looked at 5 purple airs that were deployed all across Lomé in different sites. This is a map very similar to the Accra map, and again, the pie charts show the number of days over WHO guidelines. Here we are showing the change in the PM2.5 when you correct the data from the sensor. So the dotted line is the purple air raw, and then the GMR line corrected is the solid line. So we corrected all 5 of the sensors using the same technique. And we used a co-location correction based in Accra, but now that there's reference monitors in Togo, Sonla's paper will use a correction factor developed specifically in Togo and then compare the 2. So just generally very similar to the graphs we already saw, a violin plot showing the distribution of the PM2.5 at different sites in the city, as well as an annual distribution. And I'm gonna just kind of zoom out and come out to our key takeaways here based on what we've done. So across the world, we have a bunch of reference monitors. And then we also have a whole lot of low-cost sensors. And in some places, that's great because we have a co-location, we can correct the sensor, and we can, very nicely get low-cost sensor data that comes close to a reference monitor. But what about, so great, we use the correction model and we get a co-located corrected data set. But what about all the places that do not have a reference monitor, right? Like we can't just put a reference monitor next to every single low-cost sensor. That's not financially feasible. And so to do that, we kind of create this big idea. So if we have data from Accra, Ghana, and then we have a specific point that we want to correct. But we don't have a lot of data in that regime, so we don't know how to correct it with a lot of confidence. Well, if you add in data from Delhi, India, which is another city, and then you also add in data from a third city, for example, Jakarta, the three distributions, when you combine them, it makes the beginning of a global training data set. And when you want to correct the same data point, you have a lot more data at that specific regime to be able to correct it with more confidence. And so the idea is that we would use all of these different co-locations from around the world and develop a low-cost sensor global training model. So some of this is happening thanks to the efforts of different members of the CAMSNet network. So we're collecting, cleaning, and then applying the GMR, the Gaussian mixture regression model, to these different co-locations. This model specifically is very good at identifying those different regimes. So like a high temperature, low humidity, etc. This model is very good at doing that. So thank you to everyone who's contributed already. If you haven't and you have a co-location you want to add to the data set, please let me know. My email will be at the end, or you can find me. It'd be greatly appreciated. Sometimes, the training factor we develop, works pretty well when we apply it to a different city. And then sometimes not so well. So this is still a work in progress, but we'll keep you posted on the results. And there's different steps to doing this, right? The first one is we kind of have to aggregate this data set. Then we use our model on it. And then we do some tuning to make the model perform better. We identify, what the right parameters for the model are. And then finally, you can test the performance on different cities. So in most cases, the global model is pretty good at predicting what the model would have been if the co-location was in that city. So we're applying it to like a city where there wasn't a reference monitor. So on, in some cases it's better or almost as good. But so we're still kind of exploring this, but it's an interesting idea that you could develop a co-location without actually having a reference monitor to do it with. So much lower cost than a typical co-location. So the idea is that with this global correction model, all of these low-cost sensors that are uncollocated, we would get data from them that is almost as good as collocated data. This is a big idea. Yeah. So this gives us, corrected higher quality data from about the 23,000 purple air sensors that are deployed. And then also there's other optical sensors that use the same technology as purple air. So it's possible that the model we developed for purple air could be applicable to clarity or another model that uses optical measurement. So big key takeaways: the sensor intercomparison really builds towards a better understanding of performance and helps us develop a global calibration model. The deployed sensors show us that the harmattan drastically elevates the PM 2.5 levels. And then also, it's generated by local anthropogenic activities such as traffic and waste burning. And then finally, more measurements and observations and analyses are really important for further understanding air pollution in all of Africa, which all of you already knew. So yeah, thank you to so many people in this room who made this work possible. And then on the next slide is my email. So if you have any questions, you can ask me later as well.
Thank you so much, Garima. Thank you so much, Garima, for the lovely presentation and the establishment of the models that are quite important when working with local sensors. In trying to do away with the biases that are involved with the local sensors. So for the next presenter, I'll ask Dr. Gabriel Okelo from University of Cambridge if he's ready. He's online. Dr. Okelo?
Okay, thanks everyone. I'm really glad and excited to be part of this session, and my presentation is going to look at how do we make sense of sensor data, and I'm glad to be participating in this session, and I'm also really excited to learn more about the incredible work that is being done by different researchers all over the continent and all over the world. My name is Gabriel Okello. I'm a Prince of Wales Global Sustainability Fellow at the University of Cambridge, where I lead on the Air Quality and Non-Communicable Diseases Fellowship. I am also the co-founder of the African Center for Clean Air, a research and policy center that works with policymakers and various actors to co-design context-specific interventions to address air pollution in urbanizing African cities. I'm also a visiting fellow at Okure AirQo, an entity that is leveraging on technology and AI to provide more air quality data in African cities with the aim of fostering clean air for all African cities. Now, a little bit about me. I'm an exposure scientist with a specific interest in trying to understand how air pollution affects our health and environment. I'm also very passionate in integrating the air quality research into policy, into interventions, but also into practice. And I'm also passionate about increasing the awareness of air pollution. And now a little bit of the approach that I apply. My approach is based on working together with actors within policy, within academia, in different disciplines, working with the actors in the community and businesses to conceptualize and co-design these context-specific interventions to address air quality in the various urbanizing African cities, with the aim of trying to create urban places that not only promote public health, but also support well-being. Now, I would like to look at making sense of sensor data in a holistic approach, not just the data set that has come out of our sensor. I want to look at it from the holistic project approach. And for me, this is quite important from experience, that one of the questions you need to ask yourself at the beginning is, what do you want to do with the data collected? And this is very important as it guides you through the process of data collection in whatever environment you're trying to collect it from. Do you want to understand the sources? Do you want to explore exposure between different groups, between different places? Do you want to collect the data for advocacy or behavior change? Do you want to evaluate an intervention? All this is an important process in your thought process in trying to collect data, and will later guide the process of trying to understand the data, either through analysis or through visualization or through the dissemination, as we'll see in a few slides. So when you kind of have an idea of when you kind of have an idea of the question of what you're going to use the data for, then that jogs your mind on what you actually are going to measure. Are you going to measure particles? Are you going to measure gases? Do you need to collect more information about behaviors of people? Do you need to collect data about the different microenvironments or person exposure? And then that will then take you to the actual data collection. And in the data collection, I'm glad some of the talking points I'd put down. The previous speaker, I think Garima was her name, has hinted on a few of those. Within the data collection aspect, there are quite a number of devices that are available. But have you made sure that your device is calibrated so that you'll be able to compare your data with close to the reference value, close to the true value? This calibration will also help you develop correction factors. I'm excited to hear that now you can even you can calibrate devices, or at least there's a good attempt of trying to calibrate devices that are not exactly collocated with a reference monitor within the vicinity. I think that shows how technology and really science and innovation is driving this sector of air pollution. Then you also have to think about the device placement. Where are you placing the device? If you looking at person exposure, probably placing a device in one area over a long time might not help, or you might need to apply other modeling aspects to figure out how maybe the person is getting exposed, or a group of people is being exposed over time. You need to think about which other information that you need to collect. Sometimes which is called metadata. You need to, so if you've collected, let's say, data in Accra, maybe in one city, and you're seeing a lot of peaks, peaks where there's high concentrations of a certain pollutant you're collecting. Probably it would help to make sense of that data by trying to collect possible sources that could be contributing to that. Is it the traffic? Is it near an industry? Is it the open fire burning? Then once you correct the low-cost sensors with a reference monitor, and then that really sets you off into the measurement aspect. But also, one of the things we need to put at the back of our minds is the range of these devices. Most devices, those that are measuring outdoor air pollution, you'll find that the range is sometimes in most cases lower than those that are probably doing household air pollution, or those that are doing occupational exposure. So you need to, whichever pollutant you're going to measure and the area you're going to measure, probably if you're going to measure in a household, or in households that are using solid fuel biomass, you might have to think about devices that have higher ranges. And if you're measuring outdoors, then you might just consider the devices that have a range like from 1 to 100 micrograms, or 1 to 1,000 micrograms per cubic meter. Then now, to really understand your data properly, you need to set out a process of a process of data cleaning, trying to understand what are the outliers, what are the errors. From experience, if you're measuring air quality continuously for a long time, there will be time when the device goes off. There will be time when the device is measuring, it brings out numbers that you might not understand. So you need to really have all that into perspective. Get the data set, try to understand what are the outliers. If my device measurement, the maximum is 1,000, and I'm seeing, let's say, number 99999, what would that mean? And then if they are missing data, what do I need to do with this missing data? And if there are many devices spread all over, like the previous presentation, how do you combine this data to try and make sense of it? And I've put here a figure from one of my master's students of global health, who came up with really this nice flow chart on how she analyzed that data. She was doing research in air pollution and meteorological trends in 2 Ugandan cities. And I thought, this is kind of a good way to try to walk through your data. Then you also, when you're processing your data, as you're going to the stage of analysis, then you need now to look at what summary statistics do you need in terms of do you need the averages, 24-hour averages? Do you need the averages per week? Do you need monthly averages? Do you need annual averages? So this gives you more clarity more clarity to your data, but most importantly, with the people you're going to deliver it to. If you're delivering it to a policymaker, or if you're delivering it to people in academia or people within the community, that helps you now try to jog your mind on how exactly you need to present this data. Are you going to use graphs? Are you going to use maps? This map here, I just downloaded it from the AirQo website. So this one will probably show you the concentrations of this is for PM2.5 of PM2.5 at this point in those areas, which is also a good way of visualizing the data. The next one is showing how PM2.5 is changing. These are weekly averages. How it's changing per week over over a long period of time. So you need also to kind of think through yourself on the type of data you want to present, but who you want to present it to and how you want to present it. And the third graph is the work we did with the ASAP team from the University of Birmingham, led by Professor Francis Pope. And this, we are looking at PM2.5 in kitchen concentrations in an informal setting in Uganda. But then the distinction also with this third figure is we had to collect metadata on the fuel type being used within the different households to try and understand why there's a difference within the different kitchens in the households. So I think it's very important to try and explore this in a holistic way to try and understand how do you want to visualize the data. This will help with your analysis, etc. Now, as I wrap up my presentation, I think as you make sense of the findings, it's always really key to remember your objectives. Please remember to present your data in a simple and easily digestible way, and this depends on the audience you're presenting to. Probably the way I would present my data in a manuscript could be different from the way I'm presenting it, say, to a policymaker, or could be different from the way I'm presenting it to a community. And it's also really helpful to provide feedback to the participant, because A, we get to increase more awareness, but B, we also get to learn, in some cases, the aspects on their lived experiences, and this can help build onto the way we do research going forward. The other one also I would like to really bring up is thinking about recommendations as a researcher, and this I get it from experience where at one point during my early time of researching in air quality, I would give data to policymakers, and one of them told me, "But Gabriel, for you always coming with problems, why don't you also come with problems and also try to discuss on how we could solve it?" Of course, it might be limiting because as a researcher, you might not have the capacity to be involved in all these interventions, but at least providing some recommendations, normal recommendations. It could be like, hey, from the data that we've seen, I think there is, during the dry season, there's a lot of open waste burning. There's a lot of burning of rubbish. So maybe what you could do is try to think about enforcing or stopping people from burning that. That is a recommendation you're giving to the end user. And also, it's also good to acknowledge the weaknesses in the study, because then that helps you research more on how to overcome these weaknesses. And it's really, really important to share the experiences, because then that helps also other people that are joining the research sector, or people that could be wanting to research in an area that you have carried out research. I really thank you very much. Thank you for listening. Medasi, asanteni sana. I'm happy to continue this discussion. That's my email, and really, really excited to be sharing, but also learning with colleagues that are doing very incredible work. Thank you very much.
Thank you, Dr. Okello, for the lovely presentation. I hope you'll still stay online for the question session. For our last presenter for this topic, we have Dr. Bertrand Tchanche, sorry, from Senegal.
Hi, everybody. So I'm going to talk about an ongoing work that we are doing now in Senegal. So we are trying to carry out some studies on indoor environment, and we are working on in-car air pollution at the moment. Okay, good. Okay, so I'm going to give a brief introduction before I go to the study area, and then talk about the public transport and the city of Tchanche, where we are doing this preliminary work, and then talk a little bit about the setup, give some results, and then conclude. Well, this morning we were discussing also about the air pollution in Africa, and some of the participants mentioned that some of our brothers are saying that they have been breathing without having any problem in Africa in the past. But what we can tell them also is that the population is increasing in Africa. So in the past, we had maybe, as you can see here, a few hundred millions, but now we are more than 1 billion. So as people are increasing, the environment is changing also at the same time. So this is something we can tell them also, that things are changing. In the past, we had maybe in a country like Senegal, maybe 50,000 cars, but now we are having 100,000 cars in the city. So this is changing the environment also. So as population is growing, we are having a lot of challenges. The pressure on the resource and the environment, and the rate of urbanization also is increasing. And of course, we are having a deteriorating air quality with adverse consequences, not only on health, but also on the economy and the society, and the entire society. Well, the sources of almost pollutants are well known now. So we have just naturals, and we have also anthropogenic. So in the natural, we cannot change anything. What is natural? When what is anthropogenic, maybe we can do something. Okay. So we have the burning of fuels from transport or from households or from industrial processes, from agriculture, from water treatment, etc. But when it's just coming from the Sahara, what can you do against it? Nothing. And we know the pollutants. Back, please. So what I want to point also is that it's very good that we have this meeting because what I noticed is that we have a lot to learn when it comes to air quality in Africa. And there's a need for more studies, especially on indoor environments. We don't know about air pollution in our houses, in our schools, in our buildings, in our offices. We don't know what's going on there. What's the level of pollution in houses? We don't know. Next, please. Well, we said we are going to focus on vehicles. So when we are moving in our cities like Lagos, Abidjan, and we're in a car, you feel that there's something wrong because sometimes you feel the heat or you feel that there's a fume coming in your car. So we said we are going to measure the level of pollution inside the cars and see what we have in our cars in Africa, at least for this time in the city of Tchanche. So when you have your car, the occupants inside the car can bring in some pollutants also. This is something we might know. And there are some products that bring also in the car that can bring also some pollutants. And of course, some people smoke in their cars. This happens sometimes. The car itself is a source of pollution because you have the tire degradation, you have the fumes that's produced, and you have also the pipes and the brakes also that release some pollutants that are within the car. And of course, we have the outdoor sources because you can have some activities going on the roadside, okay? Like construction works, burning of waste outside, the exhaustion from other cars, the road degradation, the tires degradation, etc., etc. So we have some sources that are outside on the roadside. Next, please. Well, we are going to go to Senegal now. Senegal is a country located in West Africa. I put it in red, as you can see. And this is a map here. It's a country of about 80 million inhabitants. And we're going to study, to carry out our study in the city of Thiès, that is something like 70 kilometers from Dakar, a city of about 500,000 inhabitants. And next, please. Well, we looked at the transportation in the city. And as you know, in Africa, we don't have our salary. Sometimes it's very small salaries, and we cannot do a lot of things with our salaries in Africa. So most of the time, we go by foot, and we don't have cars. It's not like in Canada or in the US, where people are in their cars every time. We cannot sit anyone on the streets. In Africa, it's the opposite. People are walking everywhere. We are walking everywhere. So the first means of transportation in Africa is our feet in Africa. And then you can have some systems like horse carriages that are very popular in Senegal, and also in West Africa, in many countries also. And you can have also this one, the motorbikes. When we go to Benin, Ouagadougou, Senegal now, we see young men driving motorbikes, carrying people now. So it has become a job for young people who are leaving the university and they are jobless. We have the taxis. We have these old cars that are personal cars that people use now when they are retired, and they use it also as clando, just unregulated old cars that are used for transportation also. And the city also sometimes you can have some small companies. And in the city of Thiès, we have this company that is AFTU. It's a group of owners that have come together to form an association. And each one will bring maybe 3, 4, or 5 cars, and then we have an association to build the company. Next, please. Well, that company was founded, the AFTU, because we are going to focus on the buses. We founded in 2001, supported by the government, and they own something like 2,500 buses in the country. And in the city of Thiès, we have 10 bus lines, and each line has about 8 minibuses. And they work between 7 and 8 p.m. in the evening. So one of the issues that we face when we carry out the study is that they don't have a map. There is no map for the route. And we're surprised that how are people going carrying using those buses without any map, and there is no bus stop. But the bus are having lines and they are stopping, but we don't know how. We didn't know how. So it was a surprise. So we use a GPS that we put in the bus in order to have the itinerary, and which did it for 3 lines. So we were able to have line 2, line 4, and line 6. Next, please. Well, when we're doing carrying out our studies, so this is how the bus was when it was driven. So the windows were open and the doors also were open like this, so that any passenger at any moment can get off or get in. And we chose to work on line 2, that was going from the north to the southern part of the city. Next. Well, for our experiment, we use a particle plus 8301, EQM1, a particle counter, and we use also a GPS logger. So we try to build a small system like this in order to stabilize the system, because we couldn't put our OPC anyhow. So we built a small facility like that, and then put it in a small box, and then we can attach it on the seat like this. Next, please. Well, so we made some measurements for about three days, and the trip will last something like 1.5 hours. It was something like around 11 kilometers, and we were working only on the weekday, not on Saturday and Sunday. And we do 3 set of measurement. One in the morning, another one in the afternoon, and the last one will be in the evening. Next. Well, we wanted also to know the environmental parameters during the period, and then we tried to get some data. We didn't have a ground station in the city, so we went to check the data, to take the data from the NASA platform. And we're able to have at least something to know what's going on at that time. So we can see the precipitation. We're working in the month of August, July, August, and this is August. So we can see the precipitation because it was raining for a few days. You rain for a few days during that period. And the temperature, as you can see, was between 25, but it was maybe higher than this. And relative humidity, we see that it was relatively humid during that period because here it is above 70. So, and for the wind, we saw that the wind was coming from the west, from the Atlantic coast. So this was it was given. So I can say that since we were on the ground, it was raining for some of these days, and we can confirm that. And for the wind also, we can also say, okay, it's logic because we are close to the Sahara TZ. So when it rains, it means that the humidity is coming from the west, from the Atlantic coast. We can continue. Next. Well, we look also at the driving conditions. So when we were starting, for instance, here at the beginning, it was in an area where it was flat, and we're going up, okay? And the difference was on the altitude was something like 50 meters. And also we look at the speed. So as you can see here, there's a frequent variation of the speed because the driver will stop every time. After 1 minute, it can stop. After 2 minutes. So because of the fact that there's no bus station, so that's why you can have this kind of profile, speed profile. Next, please. Well, we have recorded the PM mass concentration. This is what we had for these 3 days. So as you can see, that okay, when we started at the beginning from the first stop, when we started, you can see that the concentration is increasing on the path, and sometimes can drop, sometimes can go high and drop again, as you can see. So it's kind of charge and discharge that we are having in the bus. Next, please. Well, these are the box plot. From this, you can see that for the first day, for instance, in the morning, you can see that the level of concentration is low, and then it increases in the afternoon, and then increases also in the afternoon. So it means that during the day, the level of operation is increasing all over the day. This is what we had for in the first day. But on the second day, we see that it's almost the opposite. But this is due to the fact that it's raining that day, and that's why we are having this kind of trade. But when there's no rain, you have, as you can see, you have this situation on day 1 and day 3. Next, please. So we try also to see in which area of the city the bus is having we are having a high pollution, a high level of pollution in the bus. We try to track to see a little bit. So we are seeing that there are some specific places where we are having a high level of pollution, like roundabouts and markets of market for the section. And there's also some specific areas also, and you can also have some incidents. When, for instance, we're having an old truck passing somewhere, and we're having excess fume coming out from the pipe. This can happen also. Next, please. Well, we look also at the correlation, if there was any correlation with the temperature. And we see that in the morning, for the first graph on the morning, we have a positive correlation. In the afternoon, yes. In the evening, it was a negative correlation that we had in the evening. So it means that during the day, the temperature acts as an important factor. While in the evening, it could be it's a negative. So this means that maybe in the afternoon, in the evening, when the temperature drops, the ambient temperature drops. So, but the emissions increases, and this should be due to the traffic at that time. Next, please. Well, conclusions. I would say that this was an interesting preliminary study that we made with some quite interesting results that we had. And what we discovered, what can I say it? Something that we didn't expect is that the drivers were enthusiastic also at some point. When they were asking, oh, how many minutes have I spent on the road? What are you measuring? And we said, oh, we are measuring the level of pollution. Why? Say, no, we said, no, we can be affected if you have a lot of pollution in your car. I said, this is interesting. And when we said, okay, you are spending 1 hour and 20 minutes, and we tell them, no, this is too much. Maybe it should be half of this, because with a personal car, you are having 15 minutes, but you are having more than 1 hour for 11 kilometers. So we need to check, maybe there's something to improve there. And what we realize also is that the in-car pollution also strongly depends on the environmental conditions, because when the bus passes through polluted areas, it's seen, and the pollutants comes in. So we had also some limitations that I would call perspectives, that there's a need for us to have a ground station for weather monitoring. This is what we realized. There is also a need to monitor the volatile organic compounds also, because we felt when the bus does, there are some smells in the bus, but we didn't know what kind of pollutants we had. So maybe it's very important to have a monitor. And also, when we were measuring the period we were making measurements was a holiday period, so the traffic was not very heavy as we used to have when school are open. So maybe this also switching, because most of the customers or those who take these buses are students most of the time, and also the season. So it was raining. So maybe we have to check also during the dry season what is going on at that period. Well, this is where I will end with my presentation. Thank you very much.
All right, thank you, Bertrand. If we could have the other two speakers, Garima and Dr. Solomon, come up for the question and answer session. You can sit in the front. So I know everybody's probably quite tired by now. We still have some time for questions. So at this point, we'll take any questions. If you can say who the question is directed to, that would help, or you can just say it's directed to everyone. And there's one right here.
Hi, this is another Solomon. So the question is for Garima. In your data collection and comparisons, do you ever, or is it reasonable to consider, or is it being considered using satellite AODs for correction purposes, or do you use them at all?
Does this one work? Yeah. We've done that in the past to kind of verify the credibility of the data, and to also verify if we can use a correction factor developed in one city in a different city. So if the AOD regime is the same, temperature, humidity is the same, then we can use a correction factor to take it in Accra and apply it to Lomé. For actually correcting the low cost sensor, I don't think we've done that. And the AOD is measuring something that's pretty different from what the low cost sensor is measuring. And so I think times would have to be a little desperate for us to have to do that if we don't have a reference monitor, but it's a good idea. So we can chat more about that.
Okay, I'll come here and then I'll come over there next.
Professor Beda, my question will come in French. I know that you understand French, you can translate it before response to all people. OK? Et est-ce qu'il y a une possibilité avec cette série de mesures complexes de pouvoir trouver la contribution du cas dans lequel vous avez placé le capteur? Pourquoi n'avez-vous pas pensé mettre un capteur à l'intérieur et un autre à l'extérieur? Ça, c'est ma question. Ma deuxième question, c'est à Garima. Souvent, quand vous... Garima, you don't understand French. You are trying to speak French. Okay, let me try it in English. Usually, if you are going to give us the results of your research in Africa, you don't talk about our difficulties. What can you say? What is your point about difficulties in all countries you are working for? Thank you.
Okay. Yes, for the first question was about if you can have a kind of a source apportionment, the sources of PM in the bus. And the second part of your question was about why we didn't put a second sensor out of the bus. Okay, for the first question, well, I would say there might be a possibility to check for the sources. It means within the bus, there might be a possibility to do that. But we have not yet checked it. I think we can put it as a perspective. But what I can say first is that before starting the trip, we can make some measurement. If you have can make some measurement. And if you have also a background measurement also with a fixed station, they can help also to understand what's going on as the bus is moving. We can also put more sensors within the bus itself, because we put in the front. What is happening in the back, we don't know. What about in the middle, we don't know exactly. So maybe there's a necessity to have several PM sensors inside, and several gas sensors also inside at the same time. And also something like we didn't monitor also is the number of people inside the bus. What's happening? We have a lot of people inside, okay? Because sometimes those buses are crowded, those are they are empty. So it depends. Okay, this affects also the pollution, the level of pollution inside, and also the type of the luggage that people are taking in. Okay, sometimes they are taking the goods from the markets in, the vegetables, meat, and so on and so on. This can bring some of the pollutants also. So we have to check all these, but it's a very complex studies that is needed. We are just trying to start something for the first time like that. We don't know where we end. So we don't know exactly. We hope that we're going to continue. We'll be acquiring more sensors, and maybe at that time we could put some sensors out of the bus, okay, and then see what's happening. It's also in our plan to check the exhaust itself, what's coming out from the exhaust, okay. This is important to know, because part of it is coming also inside in the cabin. So this is what I can say for now.
Okay, I will try in French, but please help if I flop. Merci pour votre question. Dans chaque pays, il y a des problèmes de Wi-Fi, et dans chaque pays, il y a aussi des problèmes. Nous voulons plus de capteurs références, mais nous n'avons pas. Aussi, il y a des problèmes déjà d'analyse de data. Après le capteur, il y a beaucoup de data, et nous avons besoin de peuples pour analyser. Et aussi, quelquefois, il y a des problèmes de training. After you have a sensor, you have to have training to install and maintain the sensor. And that's a problem that happens in everywhere, right? Like if there's not enough people to do the training, then sometimes it can be difficult to get the sensor started and collecting good data.
All right, I'm going to go to another one, but we can come back later. Yeah.
Okay, my question is also about the use of correction algorithms, and also like a little bit of the risk that comes with doing that, because we are like training the sensor to behave as the reference monitor. And one of the problems of the reference monitor that we are talking about is that they are very scarce. They are only in some parts, and they might be, for example, look into traffic and be used to traffic, and then you are training a sensor that is picking up something totally different, for example, I don't know, like wood burning, and there is a risk on correcting the data, and then you start losing control of what is measured, what is a model. So it's a little bit of a risk there on the corrections. How are you considering that in your work?
Yeah, I'll start, and then if folks want to add to this. There's definitely a risk. So the one principle of machine learning that we use is we separate training and testing data, and that's very common in a lot of data science. And additionally, something I was talking about with the global model is the idea of building a training data set that includes lots and lots of different training data sets. And so maybe some are burning, some are traffic. And that way you're your training data is a little bit more holistic. And when you get new data to test on, the model I talked about is very good at identifying those regimes. And so there's a good chance it can kind of figure out, the regime that your new data is coming from, and identify which of the training data sets is the best fit for correcting that specific data set. That's the idea of kind of building. That's the reason that a global model could be better than just a local collocation that's only trained on like one specific type of air pollution regime.
Okay, thank you so much. I think she has said it all. Like, we have to have, at least that's when the AI comes into it. We have to train the AI to be able to get to know the reference station, able to predict the same data as we are doing the low-cost sensors, low-cost sensors away from the reference stations. So this one takes a lot of time. Sometimes you calibrate it, and then you go back and then pick data and compare, you don't get the same values, maybe closer or below. And this takes a lot of time. This is where much modeling is needed and implementing of the AI into our system.
There was a question over here. Yeah.
Thank you. My question is to my friend from Senegal.
Okay.
You made mention of temperature being positive correlated with the pollutants. And I'm looking at, for instance, CO2, where a lot of people are crowded. Since we are breathing out carbon dioxide, and we know it's a heat trapping gas. And so it should trap more heat in an environment where there are a lot of people. So I'm looking at a situation where during the day where you have people, so crowded, maybe in a bus going somewhere, they are late for work and they don't care, if they stand or sit. And so there'll be so much warming within the vehicle. So definitely temperature will increase. But some of these pollutants I know are also, they reflect heat. Some of the pollutants, I don't know. Some of them absorbs, some of them will reflect. Okay, I'm looking at it in the context of aerosols. So aerosols, some types of aerosols will reflect light back to space, and some will trap. But it is believed that those that will trap are not that much. Those that will reflect are rather more than those that traps. I'm just thinking, is it not a mere coincidence that during the day you have so many people moving around, you have so many human activities, so there will be a lot of pollutants. So definitely it will increase. There are more pollutants increasing, into the atmosphere. And at the same time, temperature, due to more, greenhouse gas emission during the day, it's also increased. So it's not a mere coincidence that during the day it is positively correlated. Yeah, coincidental relation. Thank you.
Yes. Well, I look also into the CO2. I didn't present the result for the CO2 because I was not sure of what I saw. I was not really sure about what we measured. But what I can tell you is that the trend we saw when the bus was moving was different from what we saw with the PM. It was different. So what we realized is that as the bus was moving, more people were getting in, and the level of CO2 was increasing. So we realized that we had this. And something also that's important to know is that when you're in a closed environment and you have a lot of people, they are breathing, and when they are breathing, as you said, they release CO2, and the temperature increases in the environment. If you don't open you have the window, for instance. And as I show you here on the picture, when the bus was moving, the door were open. So it helped also to release the CO2 from the bus. Okay, while the PM was entering, but the CO2 was released. Okay, and so it helped to reduce the level of CO2 inside the bus. But we still need to check to understand what's going on actually. We are going to continue the study to try to understand this, not specifically with the bus as we did, but with a personal car, where we are going to close the windows, all the windows, and where we are going to open the windows or regulate the windows, and we see what will happen inside with the CO2. But what I'm sure of is that since Senegal have a tropical climate, and it's temperatures are very high. Sometimes you can reach outside something like 40 degrees outside. So if you are in a car and you close the windows and you are briefing your people there, you can reach maybe 45. It's within the car, while you are having something like 40 out of the car. So this is something that we realized with some tests, but we didn't conclude on it. It's an ongoing study. We are starting something. Maybe when we meet, maybe I don't know, during the IQAir 2024 in Morocco, when we are trying to organize another conference or another ASIC, maybe I have more results, and I will show you what we got. Yeah.
So could we have Dr. Okello, if you're still online, would you want to chime in on any of these questions? Apologies that we didn't give you the floor yet.
Yeah, no worries. It was getting a little lonely. Yeah, but I think I wanted to comment on the previous question, not that one, on how do we balance between the data accuracy versus using the reference monitors versus the low cost sensors, and I think the modeling has really helped in trying to close that gap. So when you're looking at the issue of how close is the value towards the true value, you also have to look at the practicality of trying to get the devices everywhere. It will not be practical to have reference monitors in near every low-cost sensor. So I think we need to continue exploring methods, whether it's modeling or different types of modeling, on how we can close that gap. Because imagine that okay, we want more air quality monitoring, but imagine we have like let me just give them like 200 million air quality monitors in Africa. So that in itself will also become an issue in terms of how do we dispose of these devices, etc. So I think the modeling route is a feasible one and a practical one, given the resources that are basically available for air quality monitoring.
Thanks. Okay, so we have time for one more question before we need to go to the next presentation. So,
yeah, hi. My name is Rohit, and my question is for our friend from Senegal. So, the data that you collected, what interval was it? Number one, and was it on a stationary vehicle, or you were also taking data when the vehicle was moving? And the last question, please. The little I understand about low-cost sensors is they have a specific range of suction of air, which is about 0.5 to maximum, I believe, 0.5 liters. But when the bus is moving, the force of the air in the bus, does it interrupt in the suction of the air for the low-cost sensor? Because I believe it would be pushing more air that the sensor would be taking. Does that impact the data?
Please, I didn't get the first question. The first part of the question, please.
What is the interval at which the data was collected? 1 minute, 5 minutes, 10 minutes?
1 second.
1 second.
Yeah.
Perfect. Then the second question is, the data was collected in a moving bus, right?
Yes.
So then if it is in a moving bus, the sensors are designed to inhale a specific amount of air per minute, right? Low-cost sensors. And when the bus is moving, I'm sure there's a force of air inside the bus because it's an open environment. The windows are open. Does it impact that flow rate of the sensor? And if it impacts, does it make any difference on the values?
Well, we are not investigated that. From what we saw, I saw you the speed, because the speed here is also important. Okay, it's really important. The speed of the bus was about, this is the average, the average speed was about 7 meters per second, 7 kilometers per hour. So it was not moving very fast. So maybe the intention is not very big, okay? But if you are moving faster, like 100 kilometers, I'm sure it will have a large effect on the measurement. But here it was, but we have to check. But we need to check the effect of the speed coming in. Yeah, but by putting maybe by measuring also that's the speed of the air, because the speed of the air coming in and the speed of the bus might be different. Also. So it is a very complex study that we are starting here. As I was saying, we need a lot of equipment in order to do that also. And as you saw, we had a limited means of measure. We had just this sensor that's a very good sensor. This particle plus, this is a very good sensor. It has a very good accuracy, but still we need maybe more, several like that, one out, maybe several inside, in order to understand fully what is going on. And also something that I didn't say also is that sensor help also to measure on different channels. So we could have something like PM5, PM10, PM1, etc. But I prefer to talk about PM2.5 because otherwise we have a lot of data to present here. But I chose not to present that part also. We can still have a discussion after during the break or during the when we are free.
Yeah. All right. So with that, let's thank our speakers one more time. And then I'll hand it back to Tony.
Thank you.
Okay, so the next thing on the agenda here is that the exhibitors are going to talk about their stuff for a few moments. The first one is IQAir. Christi Schroeder.
Hello, everyone. Thank you very much for the opportunity to speak with you during this exhibitor presentation session. My name is Christi Chester Schroeder, and I am the Air Quality Science Manager at IQAir. And today I'd like to share with you how IQAir is working to revolutionize global air quality monitoring with low-cost sensors and information technology. IQAir is a family-owned Swiss-based company with 60 years of experience in air quality technology. In 1963, IQAir introduced an air filter system for residential coal ovens to help reduce black dust buildup and mitigate asthma flare-ups during winter months when coal ovens were used for residential heating. Over the past 60 years, our mission to empower individuals to protect their health by limiting exposure to air pollution has expanded to a global scale. Today, IQAir operates the world's largest free real-time air quality information platform and engage a growing number of global citizens, organizations, and governments. In addition to providing real-time free global air quality information, the platform also serves as a turnkey solution for the creation of low-cost air quality sensor networks, providing both air quality monitoring hardware and fully integrated data management solutions via our mobile app and web-based dashboard. The extent to which air pollution impacts humanity is really quite staggering. A 2018 study estimated that 8.9 million deaths globally could be directly attributed to long-term exposure to PM2.5. A report released in 2019 attributed 1.1 million deaths in the continent of Africa to air pollution, as well as an estimated economic output loss of nearly $5 billion in Ethiopia, Ghana, and Rwanda due to air pollution-related disease. Reducing the negative impact of air pollution is a complex and multifaceted problem, but the starting point for any proposed solution is the same: obtaining comprehensive air quality data. Any program or policy to combat air pollution by limiting personal exposure and or reducing emissions all start with the development of monitoring networks that generate data that can be converted to information and insight to drive impactful decision-making by both policymakers and individuals. At IQAir, our goal is to connect air quality data sources to individuals and organizations who need it. Our platform is sensor agnostic and hosts data spanning from government reference monitors to multiple different makes and models of low-cost sensors. We stream data from more than 25,000 ground-based monitors and partner with many collaborators, including the UN Environmental Program and Greenpeace, to maximize the visibility and accessibility of global air quality data. This map shows the global distribution of ground-based air quality monitoring stations producing publicly available air quality data in 2022. The disproportionate coverage density is really pretty readily apparent and highlights the very real need for affordable air quality monitoring solutions. Just anecdotally, the city of Los Angeles has more sources of real-time air quality data than the entire continent of Africa. Given the low cost points and ease of deployment and significant reduction in operational costs, low-cost air quality monitors are increasingly becoming a viable public alternative to those countries that lack government-operated air quality monitoring stations. The need for low cost point, easily implementable option for the creation of an air quality monitoring network really drove the innovation around IQAir's ambient air quality monitor, the Air Visual Outdoor. Here in this exploded diagram, you can see that the monitor has a modular design with the capacity for 4 independent plug-and-play sensor modules that are easily field swappable. The base model has multiple networking options, including a Wi-Fi option and LAN option to ensure optimum data recovery. There are also additional hardware options available to make the monitor completely infrastructure independent. In many global locations with monitoring needs, there can often be a limited accessibility for power and internet coverage. So we offer a solar kit and a pre-configured cellular modem that really truly allow for deployment anywhere and make the monitoring device completely infrastructure independent. IQAir's Air Visual app is easily utilized in the device installation procedure to network and register the monitor. It guides the user through a very detailed step-by-step procedure in how to install the monitor and register the device with your account and to bring it online. Through the app, you can also choose to publish your monitor's data online in the AirVisual platform to make it visible for anyone to see. Part of our data quality control procedures require users to take pictures of their device installation in an effort to ensure the quality of the publicly available data the monitor is providing to the global community. Data from your device can be seen directly in your app, and device information can be seen there as well. Push notifications delivered through the app are utilized to alert a user when there may be a problem with their device. They provide troubleshooting guidance as well as the ability to deliver customizable alert notifications, such as when a pollutant concentration threshold has been exceeded or when a device goes offline. Just this past summer, IQAir released a brand new web dashboard interface that provides users with expanded, really powerful tools for network administration. The free version of the dashboard offers users access to real-time and historical device data, device map views, access to device settings, and data export options for users who become contributors by making their monitored data publicly available. The paid version of the dashboard provides crucial tools for network administration, including organizational tools such as grouping devices into subnetworks with the workspace feature, reassignment devices to different users or different workspaces, the ability to invite, add, or modify users to access your monitoring network, customizable email alerts, and expanded data export options. Making air quality data publicly available is really at the core of our mission, and we offer some additional data display features in the dashboard that users can utilize to share their data. One really fun one is the ability to create widgets to embed in websites. Here you can see a screenshot of our dashboard where you can configure different options for a widget you'd like to create, either for your specific device, or you can actually do it for a city or a particular station as well. Here's a couple of examples of device data-based widgets that you can create. Other options that we include for information displays for your data are the ability to create TV displays that can be used to display data on monitors or even billboards. We have a lot of groups that have indoor and outdoor monitors, and they display their air quality in their lobbies of their businesses. So when people come in, they can actually see the quality of the air that they're breathing inside the building, and see that compared to how it is outdoors as well. All of these tools really provide an end-to-end service for air quality monitoring with a low-cost sensor network. These tools are very user-friendly and enables the collection and dissemination of high-quality data and information, which is incredibly important because the scope of potential projects involving low-cost sensors is really very expansive. The minimal skills required to utilize these tools make them very accessible to all levels of users. We have a very active organization in South America that we work with that installs sensors in preschools and then brings together the community to develop local policies and interventions to limit children's exposure to air pollution. This infographic showcases some of the success metrics of the network's interventions in Lima, Peru, that are really powerful examples of using air quality data to create positive impact on the local communities, really at that very hyper local community level. As low-cost sensors continue to revolutionize air quality monitoring around the world, IQAir really continues to work diligently to democratize air quality data that can drive forward the conversations around the importance of air quality information that empowers individuals to take action to limit their risk and adverse health consequences from exposure to air pollution. Thank you very much for the opportunity to speak with you today. My colleague Cliff is here at the conference with you and can help answer any questions that you may have. More detailed information regarding our monitors, the Air Visual app, and the IQAir web dashboard can be found here. Just grab a picture of these QR codes and they'll take you right to the website where you can find additional information. Thank you so much for your time and attention. I really appreciate it. And I hope you all really enjoy the rest of the conference, and be sure to talk to Cliff about IQAir. Thanks, everyone.
Thank you, Christy. And so in the next room are the exhibits, including an IQAir exhibit. So you can spend some time, maybe later today, or if you're tired, maybe tomorrow, and head over there and check it out. Our next presentation is from Clarity.
So I'm Lee Swanson. I'm the regional account manager for Clarity. Clarity is a Californian company registered in Berkeley, California. They were founded in 2014. And it's a very mission-driven company where we want to sort of scale up and give organizations and governments the tools they require to provide the data for air quality. So we've now got active sensors in over 70 countries around the world. Some of these are the larger projects that we're involved in. So Breathe London, we've got over 100 sensors in Bay Area, California. We've got over 400 sensors now in Sydney and Australia. So we operate all over the world. So we're on 70 countries in 6 continents. So I'm going to power through this because I know everybody's tired. So we've pioneered what we call sensing as a service. So this is everything is included within our service. It's a package. So you get the hardware, which is the Clarity Node S. You can have a look at it next door. We've brought a couple of demo models, and you get access to the Clarity Cloud, which is the dashboard where you can view the data. And then beyond that, there is the Clarity Expert Support. So we have project managers, we've got software engineers and environmental experts to help people understand the data that they're seeing. So this is a picture of the Clarity node. So as standard, it's solar powered, which makes it very easy for deployment and to move around to different locations if needed. It can also run off hardware power if there's areas that solar power might be an issue. The solar power charges an internal battery. So in the event that the solar power becomes disconnected, there is a backup battery which will last anywhere between say 10 and 30 days, depending on various issues, ambient temperature and sampling rate. It's a cellular connectivity, so globally cellular connectivity, so it doesn't rely on Wi-Fi, and it's UV and weather proof. There's some of the you might not be able to see this at the back, but we've got some technical specification flyers next door, but it measures PM 2.5 and NO2. This is an important thing. So the Clarity nodes, they're not designed to replace reference monitoring stations. They're there to supplement the reference monitoring stations. I know there's been a lot of talk earlier on about calibrating the sensors and particularly in reference monitoring stations, but it's important to point out that they're not there to replace the reference monitoring stations. They're there to supplement them. As has been mentioned earlier on, the reference monitoring stations can cost tens of thousands, if not hundreds of thousands of dollars, whereas for the same cost, you could get a larger network of low-cost sensors. So this is just an example of the Clarity dashboard. So here you can configure your nodes and check the sensor status. You do get automatic emails if there's an issue detected with the nodes. You can view and plot and download the data. You can assign user roles. So different people within your organization can have different access rights. So if you want people to just only view the data, or you can have other people that can configure the nodes. And the data it can also be accessed via an API. So if you wanted your own customer-facing website, then the data can be uploaded to that customer-facing website. So it doesn't have to be via the Clarity dashboard. So, and then I've mentioned already about the Clarity Expert Support. So it's included. So we operate a subscription model. Typically, most low-cost sensors operate under that model, but within that, you get the hardware, you get access to the cellular, to the Clarity dashboard, but then you also get access to the full backup support afterwards, as I mentioned. So you get a dedicated project manager. You would get access to software support if needs be. A lot of the people that work in Clarity are environmental experts. They have like MBAs and degrees in environmental sciences, environmental management. And then just to talk about Breathe London, I know a lot of these projects coming out now at the moment, they have Breathe at the start of them, and there's Breathe Cities coming out. So Breathe London, I think, was probably the first sort of one to be called Breathe London, well, Breathe City. And we've now got, I think it's now approaching 450 sensors, and it's a hybrid network. So it's part funded by the Greater London Authority, part funded by Bloomberg Philanthropies, and part funded by like the local councils within there. So it's a network made up of hundreds of different sensors, and they're all used for different reasons. So community groups, they might be concerned about the pollution within their community. So they will either apply for a node, or they might self-fund it themselves. And then the local authorities, obviously, they'll be interested in pollution within their areas. It was from the Mayor of London, Sadiq Khan. He really wanted to give people access to air pollution data within London, and that was sort of the reasons that sort of grown from Breathe London. It started off with only 195 in 2021, and as I said, we're up to nearly 450 sensors now within the network. Yeah, it's the data is used. The latest round of funding, so DEFRA provide funding for air quality projects, and some of them were so students could generate a walk to school map and avoid the most polluted areas within London. So it's just many different ways that the data can be used. And then just an idea of some of the partners and like companies that Clarity have worked with. For me, yeah, it's good to sort of be here and see some people in person rather on just a little Zoom screen. So yeah, thank you very much.
Thank you. Okay. Our last speaker is from AirQA or AirQO. Is the speaker here?
Thank you. That's actually AirQo. Yes, my name is Diop Okure, and the program manager and air quality scientist at AirQo. So this is actually going to be presented by one of our young engineers, the exhibition. So AirQo, could I have the slides? So AirQo is based at Makerere University, that's in Uganda, at the College of Computing and Information Sciences. So the broader aim really is to contribute towards tackling the challenge of urban air pollution in African cities, but more specifically while leveraging digital innovation and technologies and advances in technology. So to build capacity. So our work is really centered on gravitates towards two broad themes. One on building capacity. Could you go to the next slide? So the mission really centered on two, as you might see there, on two broad themes: building capacity for local capacity, in Africa, for air quality monitoring using local sensors. In other words, we want to make local sensors work in African cities. The next theme really is to explore the effective avenues to use the data to accelerate action. But for this particular presentation, it's really going to focus very much on the first theme, which is on the data technology, data infrastructure, and that is going to be Anold. Could you go to the first slide again? Sorry. No, the previous one. The very first slide. Yes. So yeah, talking about or exhibiting really on the digital, custom digital solutions for sustained air quality monitoring in African cities. Some keywords there: sustained monitoring, not pilots. Anold, you can take it away.
Thank you very much, Dale. Yes, my name is Anold, and we are going to talk about the low-cost air quality monitor, specifically built, tested, and calibrated for the African environment to withstand any changing weather conditions and ensure data integrity, but data access for all. Next slide, please. So the device is, first of all, made for Africa because it's locally manufactured, calibrated, and tested within the African environment. Because of the changing and current limitations within the different African communities, the device is made to be powered by both solar and electric sources, depending on the need, but also due to the lack of communication infrastructure in some of the communities. For example, in most of the areas where data is most important, you'll find that we don't have access to Wi-Fi. So the devices have been made capable of transferring data using cellular means. But also, as part of the quality assurance, we work in conjunction, or we test these devices along with reference devices like the BAM 1022 to ensure that the data integrity is given out to every community member. The device is portable and therefore is capable to be used for static and mobile means, which have actually been tested. And one thing very good about this AirQo device is that it's completely recyclable. First of all, its casing is 3D printed, which increases testing, eases iteration, but this is also biodegradable. Then for the PCB inside the device, we can recycle it in many ways. So for example, we look at some of the current limitations in accessing data from reference devices. With our PCB, we can actually enable communication with reference devices like the BAM, whose data is costly to access. And then you'll be able to access that data through customized dashboard. Next slide, please. So this is our sensor kit, which is easily installable. It comes with 2 solar panels in case of lack of electricity access. And it has mounts, which makes it capable to be installed on flat and rounded surfaces. Next slide, please. So this is an example of the visual of the installation. It's very quick, even to someone who is afraid of assembly and electrical components. And this is how the whole installation looks like, but it's made in such a way that you can actually install it on any flat surface. But obviously at AirQo, we work to ensure that a device is placed in a situation that enables 360 degrees air access. Next slide, please. Yes, now we talk about the custom digital solutions for network management and data sharing, because we start with the device, but what happens when we collect the data? So as part of our network management, we monitor data from the devices in real time. Therefore, we are able to, in real time, assess the quality of the data coming in. Our devices are made with 2 sensors, and hence we are able to compare the correlation and know when something is not right. For example, on the sensor correlation graph, you can see, and we have set thresholds of 0.99. So when we observe a low threshold, we can actually know that something is not right, and we start analyzing the data further. But also on the side, we can see here, data has just come in 44 seconds. We can also look at those parameters and further analyze them. But to add with what we have on our platform is that we can also track the maintenance logs to actually analyze what could be the possible causes of failure in a different site where the device has been installed. But this device is well made to fit in the African setting, and we literally have little cases of failure when we install. So we have a dashboard which shows the coverage of low-cost air quality monitors across the different African cities. But the dashboard also has access to some of the reference devices which have free data access. On the middle picture, we can see someone looking at our mobile app, and what it comes with is that it enables not only real-time data, but you can also be able to forecast. Actually, this is for Independence Avenue, Ghana, and it shows that air quality tomorrow will be moderate. Next slide, please. So as part of making our data accessible, actually in part of our mission is to work with partners and ensure that air quality data is accessible for all. And what we pride of is seeing that we are getting more air quality champions, and even people who knew nothing about air quality are now starting to embrace the need for change. So we have our API, which enables customized integration and personalization. On the picture on the left, we see currently one of our local channels in Uganda, which after news, enables the communities who don't have access to mobile platforms and dashboards to know about air quality trends in their regions. But also on the right, we have a picture that shows the launch which happened in Nairobi, Kenya, showing the seamless integration of the AirQo API to enable data access for the Nairobi city. Next slide, please. Thank you.